Alright, hi everyone. Welcome back to the second F equals MA club meeting. Today we're going to be talking about dynamics and F equals MA exclusive materials. And so today's lecture is going to be a lot more different from last time's, since last time I really just didn't enjoy the format. I was kind of just talking for an hour and 20 minutes. And so this time it's mainly just going to be this and a worksheet. And if you're just here for the problems, I think I'm going to add chapters so you can just look for whichever problem you want to look at. So let's get straight into it. So just some basic review. Last time we talked about basic kinematics. We talked about projectile motion along with the F equals ma equations that you absolutely need to know. We talked about interpreting position, velocity, and acceleration graphs, and we talked about relative motion. And if you want to look into these, if you aren't looking in the playlist, it's probably just in my channel. If you are in the playlist, it's probably just going to be the video straight about this one. So let's get straight into it. Today we're going to be talking about dynamics. So the main thing that we just need to follow, remember that dynamics is going to be referring to kind of an expanded version of Newton's second law, which is F, or like net force, equals our mass times our acceleration. And if you're ever curious about what the equation is, you can just look at the very top of your exam and check the title. And so if you really want to learn more about dynamics, I would recommend you just search up and look more into it, as these lessons are more going to be focused on and just pretend that you already have a basic understanding of physics 1. And so the forces that we need to know about are normal force, tension force, frictional force, and gravitational force. Remember that normal force is always going to be perpendicular to our contact surface. Remember that our tension is always going to be along our string or our rope. Remember that our frictional force is always going to be opposite of whatever direction our object is moving in. And remember that our gravitational force, in dynamics at least, is always going to be vertically downward. We're going to talk more about Newton's fourth law, about universal gravitation and stuff like that in the future. But for the sake of dynamics, it's always going to be pointing vertically downward, or whatever, in the direction of the Earth's core, which is going to be typically downward for these problems. Just one more extra thing, and this is going to constitute to basically just one or two problems, but remember that measured forces, the forces that scales measure are always going to be measuring the normal force that is on the scales. So if you're getting 50 kilograms that on your scale, that means there's 500 newtons acting on that scale, or at least there's a normal force of 500 newtons on that scale. And so the main things that we need to know are circular motion and inclined planes. And so circular motion, our big equation for now, is going to be v squared over r is going to be equal to our centripetal acceleration. And by that logic, our centripetal force is going to be mv squared over r, because force is equal to mass times acceleration. This is going to be our tangential velocity. We're going to learn later about rotational velocity, rotational inertia, and all that stuff. But for now, this is the simplified stuff. So, yeah, that's circular motion. And inclined planes, we just need to know the components. Remember that our gravitational force is basically split into two components. One is mg cosine theta, which basically amounts to normal force most of the time. We also have an mg sine theta, which is pulling our mass down the ramp. And we typically have a frictional force. Remember that our frictional force is going to be acting in the opposite direction of whatever direction our mass is moving in. So if our mass is moving up, that means that our frictional force is going to be moving down the ramp. And if our mass is moving down the ramp, then our frictional force is going to be moving up the ramp. And remember, our frictional force is calculated by our frictional coefficient, also known as mu, times our normal force, which is calculated through that. And so here's where we get into the F equals to MA exclusive material. The first thing that we need to know is dimensional analysis, and basically what this means is, or at least what this constitutes in the competition, is they're going to give you one of these, a few of these dimensions, let's say length, mass, and I don't know, velocity or something, and they'll tell you to find a different dimension such as force, and what you have to do is just deduce the combination that'll give you force. So let's say we're talking about the length, mass, and our velocity, right? And we're told to find force. We know that our end product is most likely going to be mlt to the negative 2. So that means we're going to have to square velocity to get t negative 2. Then we're going to have to divide by L to get L, and then we multiply by mass, and that's going to give us our force. So that's how dimensional analysis works. I'm going to explain it a little bit more once I get into the worksheet. Next, we have error propagation. We have addition and subtraction, multiplication, division, exponents. The basics of this is that if we're given a function, our uncertainty is going to go by this. And this is the calculus interpretation. It's just best to memorize these formulas, and we're going to get a little bit more into this later. And there's one thing that this doesn't cover, and we can switch to Krita, which is, oh no. The one thing that this doesn't cover is average. So the point of average is if we were to measure something n times, let's say, if we were to measure something n times and take the average of it, then our uncertainty is going to be multiplied by a factor of 1 over square root of n, which means that our uncertainty basically goes down by this rate. And yeah, so that's the one thing that this doesn't cover. And if you want to learn more about it, again, you can look online, and if you guys really want to, I'll probably provide a textbook somewhere. And so that's error propagation. And finally, we have a few of our basic F equals MA strategies. We need to know how to remember to break down any hard problems, since most F equals MA problems are going to look very intimidating, but remember to split everything down to its basics and solve everything from there up. Remember to solve for limiting cases. If you're given something that depends on, let's say, an angle or something like that, or like a sine, cosine, remember to test like sine 90, sine 0, and see if the answers make sense. If they don't, cross them out. And if you get something like let's say something about collisions or something like that, test the very edge cases. And third and finally, don't overcomplicate problems, but also don't be tricked by the very, very easy answers, unless you're probably starting out, in which maybe there's one or two of those. And yeah, so we can get straight into this. So let's just start. Oh no, I'm being exposed. So let's go back in here. So let's talk about our first problem now. A sled is loaded with children. Starts from rest and slides down a snowy 25-degree incline, traveling 85 meters in 17 seconds, right? And we're told to try and find the kinetic friction. So let's get straight into this once I'm able to work this out. All right, so let's go here. So I'm gonna hide this for now because last time was such a pain. But yeah, so we have a 20. Oh no. We have a. Please work with me. We have a 25-degree incline, right? 25-degree incline. We travel 85 meters in 17 seconds, and we're told to find the frictional coefficient. So something that a lot of people might say is, oh no, Joey, where's the mass? Where's the mass? We'll get into that later. Let's first deal with our acceleration. So if we take into account one of our old and friendly kinematic equations, we know that our displacement is going to be equal to our initial velocity times time plus 1 over 2 times our acceleration times our time squared. Since we start from rest, this is basically not needed, and so we know that our displacement, which is 85 meters, is going to be equal to 1 over 2 times our acceleration times our time, which is 17 squared. So our acceleration is going to be equal to 2 times 85, and we can just deduce that by multiplying 2 divided by 17 squared, right? And if we do that on a calculator, I believe this is going to be around 0.588. And if I were to plug that in right now, yeah, around 0.588. So our acceleration is around 0.588. Yeah, meters per second squared. Okay, so that's our acceleration, right? Next, we're told to, let's go into the inclined plane part. So, let's first get an inclined plane down. We have a 25-degree incline, right? Let's draw the components of this. So first we have our gravity, right, on our sled. Let's say this is our sled. This is our children in a very tight, very nice box. This is our gravitational force. This is going to be our gravitational force cosine theta. And this is going to be our gravitational force sine theta, right? Ooh. So this is going to be our normal force, and this is going to be our frictional force. And we remember that our frictional force is going to be our frictional coefficient times our normal force. Wow, my thing is not calibrated today. So I'm going to make this smaller. We can now deduce our equation. Remember that we do have an acceleration. So our net force is going to be equal to our downward force, which is here, our mg sine theta. And we have a force in this direction, which is going to be our frictional force. So minus mu times mg cosine theta. And what is our net force equal? Our net force is equal to our mass times acceleration. Haha! This is where the magic of that mass thing comes in, because we can just cross out mass on all sides. So our equation is going to be g sine of theta. Well, I could put this in parentheses. G times sine of theta minus mu cosine of theta is going to be equal to our acceleration, right? And if we just plug all this in, we know that this is 10 because of the magic of the F equals ma competition. So we can just multiply our acceleration by 10. We know that our theta is equal to 25. So mu is going to be equal to our acceleration divided by gravity. Wait, no, I'm doing this wrong. So we have our sine theta, right? Sine theta minus acceleration over gravity, and this is all divided by cosine of theta. And we know our theta is 25, so if we just do this on our calculator, sine of 25 minus 0.588 over 10 divided by cosine of 25, and that is going to give us our mu k, which is going to be around 0.401. And the closest answer to that on our sheet is going to be here, which is B, 0.4. All right, and let me just clear this out. All right, on to our next question. So what is this? All right, so a block of mass 3 kilograms slides down one ramp and up a second ramp. Coefficient of friction is 0.4. It begins at a height of 1 meter, down a 30-degree incline, and goes up another 30-degree incline. And so, to what height does the horizontal, above the horizontal, does the block reach above the second ramp? So, let's go back here. And so we can first draw a diagram of this, right? We have our diagram, which is, we have 2 ramps, right? 2 ramps. We have one here, and we have one here. Let's just say it looks like that, right? We have a block. Oh, we have a block up here. Oh, wow, this is a well-drawn block. We have a block here. It's moving down. There's a frictional force on both of these, and it's asking us, remember these are both 30 degrees. This starts at a height of 1 meter, and it's asking how far, what height it gets up to on the second ramp, right? And so, just give me one moment. Yeah, okay, so technically we can solve this with conservation of energy, and we absolutely should. I'm just too stupid right now to actually do that, and I also did this while I was basically in like 30 minutes, so a lot of these questions are not too good. So, let's first calculate our acceleration down the ramp, right? Okay, so we first have our mg, remember our components, we have mg, we have our mg cosine of, no, not cosine theta, mg sine of theta, right? Minus our mu mg cosine of theta is going to be equal to our mass times acceleration, right? So, if we were to calculate this, remember, we can just eliminate our mass for now. Just cross these out. Remember that this is going to be 10 sine 30 minus, what is this, 0.4 times 10 cosine of 30, right? So this is going to give us an acceleration of around it's going to give us an acceleration of around 1.54 meters per second squared, right? Our distance along the ramp, remember this is a 30, 60, 90 triangle. This is 30, this is 1, so our side length is 1. Remember that this is our ratio. So we're going to be going down 2 meters. Remember that this is our acceleration. We can use our formula, delta x. We can use this formula, right? Vf squared is equal to our initial velocity squared plus 2ad, right? So going from here, we have our initial velocity, which is 0, plus 2 times 1.54 times 2 is going to be equal to our final velocity squared. So we could just do 4 times 1.54 and take the square root of that. And that's going to give us a final velocity of around 2.48, right? So now we need to know what height this reaches, right? So now we need to find the acceleration of this. So we know that our frictional force is going to be pulling us back, and our gravitational force sine theta is also going to be pulling us back. So for here, let's see if I can first shrink this. So just select all this. And what was I going to put here? It was this one, not that. So we can move this here, move this here. So now we can start going even more. So for this portion, right, our net force is going to be equal to our negative mg sine theta minus mu mg cosine of theta is going to be equal to mass times acceleration. Remember, we can cross these out again, and so what we're going to get is negative 10 sine 30. So we can just take our old equation and just add a negative in the front. So negative 10 sine 30 minus 4 cosine of 30 is going to be equal to, and if I can write this down, our acceleration is going to be negative 8.46, right? Meters per second squared. And so, given that our velocity is that, we know that our, what equation should I use? Yeah, so we can use this kinematic equation. Our delta x is going to be equal to our initial velocity times time. Oh, wait, Oh, yeah, we can just use this equation. Sorry, this is first time as well. So we can use this equation again, plus 2ad. Our final velocity is going to be 0. So our initial velocity squared is going to be equal to, since we have a negative acceleration, this is just going to be equal to 2 times a times d, with this being positive. So our initial velocity squared, since we're trying to find our distance is going to be equal to v naught squared over 2a. Our v naught is actually going to be our vf from here. And so that is going to be equal to 2.48 squared divided by 2 times 8.46, right? And so that's going to give us a distance of around, this is going to give us around 0.36 meters, right? And so at this point, you might go, hey, Joey, that's not one of the answers on the worksheet. Haha, screw you. It's because we were measuring this distance. We were not measuring this height, right? So our height is going to be, remember that this is our 30, 60, 90 triangle, right? Don't mind this. So this is going to be 1 square root of 3, 2. We know that this is going to be 0.36 meters. So this side length is going to be 0.36 divided by 2, which is going to be 0.18 meters. So we rise to a height of 0.18 meters. And if we look back on our worksheet, that is shown to be our answer 8. So yeah, there's that. Oh no, I'm being exposed again. Oh no. Okay, click on that, click on that. There we go, that works. So, moving on. Problem 3. This is a little bit more difficult because it's more conceptual than anything. But once you figure out the basic concepts, it's trivially easy. So we have a point object of mass m hanging off the ceiling of a car on a string of length l. It is observed to make an angle theta on the vertical as the car uniformly accelerates. So find the acceleration of r in those terms, right? So let's switch back here. So the basics of this is that we just have our mass, right? We have our mass here, and it's moving in. Oh no, I am going to absolutely use the line tool today because my hands are apparently broken. Please, 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 pretty please. Oh, you're why? Pretty please, thank you. So we currently have a mass here, mass here, that is making an angle theta, right? So if we were to break down the components that are currently acting on this object right now, we have our gravitational force, and we have some acceleration that is caused because, think about it this way, when you're in a car and you step on the brakes, you move forward, right? And when you slam on the gas, you move backward. And so that's going to be the same acceleration that the car has. So we can make this into almost another triangle, right? And so we have, this can just be our vector components, right? So we have this, and we also have an angle here, right? So this is going to be it's going to be the force caused by gravity, right? And we're also going to have the force caused by our car, and this is going to be total, and this will have this same angle theta. So in order to find this side length, we can just cross out these m's, and we can and which trigonometric equation takes the opposite and adjacent to find the hypotenuse. Takes the opposite and adjacent. That is going to be our tangent. So our tangent is going to give us opposite over adjacent, right? Since we're given our adjacent as g, so we're just going to take g tangent of theta is going to be equal to our a. So that's how it works. This is probably a little bit flawed of an explanation, but it's the best I got. So let's start moving on to the next problem, right? So next problem is going to be the measured scale problem that I was talking about earlier. So you have a scale that's calibrated to give a correct reading on the ground. When a person holds it and presses on it both sides, it pushes down. The left hand exerts a force of 200 newtons, and the scale has a mass of 5 kilograms. So it's asking for the reading on the scale, right? Okay, so we have a scale. When it's on the ground, it gives a correct reading. And remember our entire thing, which is that our scale is going to be measuring our normal force, right? So the really tricky thing about this is that the scale already has its own weight, right? It's going to have an mg, and this weighs what, 5 kilograms? So it's already going to be exerting a force of 15 newtons, right? So like even if we have nothing on this scale, our normal force is already going to be 15 newtons. But since this provides a correct reading, it's going to give you 0 kilograms right now. All right, let's just say that this is our little display, right? It's going to measure that 0 kilograms. So we know that our scale is automatically going to basically subtract 15 newtons wherever it is, because it's always going to assume that it has that force pointing down. However, now we have a very interesting dilemma, which is that our force is currently being held up by our left hand and our right hand. So it's automatically going to be subtracting 50, but it kind of doesn't have to. So we currently have a left hand and a right hand, and our left hand is exerting a force of 200 newtons, right? So our normal force is going to be equal to 200 newtons, right? Because our force is just pointing in this direction. However, that is not going to be our reading because we have to subtract 50 newtons from every single reading that we get. So we have 200 newtons minus 15 newtons is going to be equal to 150 newtons. And remember that we have to divide by 10 to actually get our mass since we're on Earth. And so 150 divided by 10 is going to be equal to 15 kilograms. And if we look back at our document, that will be our answer 8. I should probably set this to viewing. All right, that makes things easier. So next problem, Also an easy one, conceptual. This is going to be about circular motion. All right. So we have a car that is currently going around a circle, moving at constant speed, right? So its net force is going to be equal to 0. And we also have a balloon filled with helium, right? So let's go back here. So we have a car that's going around a loop, right? That's the basis of this problem. Please work with me. Please work with me. There we go. So we have a car that is currently moving in a circle. Beautiful circle, if you couldn't tell. I know how to draw circles. We have a car. It's going around a circle, and it has constant speed. It has constant speed. This means that its its net force is going to be equal to 0 because its acceleration is going to be equal to 0 since our velocity is a constant, and we can go back to calculus or whatever, but this is the basis of what this is talking about, right? So that means that that our car is basically going around, and it's going to be having some force and some well, not that. It's going to be consistently moving forward, and remember we have our centripetal force that's pulling it in, right? This is going to be mv squared over r. Remember that? So that means that the force that is currently acting on the balloon, which is inside the car, is going to be in this direction, which means that our answer is going to be D, right? Because our centripetal force is going to be moving in this direction, which means our balloon is also pulled in this direction. If we think about it like that, like this here. Yeah. And this is inside our handy dandy little boxcar. Here, I'm going to stop drawing. I'm running out of time already. Let's just erase all this and go back to our problems. So next one is going to take a little bit more time, but in the end, it's also not too hard of a problem, not too difficult, which is pretty nice. So we have a 22 kilogram suitcase, right? Being pulled in a straight line at a constant speed of 1.1 meters per second. The student pulls with a force of 100 newtons at a 30-degree angle, respect to the horizontal. We're told to find the coefficient of friction again, right? So let's think about it this way. So again, we have a constant velocity, right? We have a constant velocity of, please work with me. No, okay. We have a constant velocity of 1.1 meters per second, right? This doesn't change. So that means our acceleration is going to be 0 meters per second squared, which means that our total force, is going to be equal to 0, right? Our net force. This also means that our net force in the x direction is equal to 0, and our net force in the y direction is also equal to 0. So let's draw a little free body diagram, right? So we have a 22 kilogram suitcase. We can just say a 22 kilogram mass that's being pulled by a force at a 30-degree angle, right? Oh no, 30-degree angle. So we can split this force into two components, right? We have our force cosine 30, force cosine 30, and we have another upward force of F sine 30, right? So let's split these up. Let's first talk about our y. Remember that our net force in the y is going to be equal to 0. So what forces are going to be acting on it? We have our downward gravitational force, and we have our upward normal force, right? And our normal force is going to be really important when we're talking about friction, because remember, our friction is going to be mu kn. So let's first find the net force of the y. So we have our gravitational force, we have our normal force, and this is something that really trips people up a lot of the time. We have this F sine 30 as well. So our F sine 30 plus our normal force is going to be equal to our gravitational force, because remember that these are in two components. So that means that our normal force is actually going to be equal to our gravitational force minus our force sine of 30. It's not just going to be our gravitational force. And if we do this, remember that this is 100, this is 220. So 220 minus 100 times 1 over 2, since sine of 30 is 1 over 2. Our normal force is going to end up as 170 newtons, right? So now it's time for our force in the x direction. So Since this is also net zero, we know that our force cosine of 30 is going to be equal to our mu k n, which is now we know 170. This is going to be 100 times the square root of 2, and if we just do 100 square root of 2 divided by 170, we get our coefficient. Oh, wait, no. Oh, whoopsies, that's not square root of 2. I'm an idiot. I'm so sorry. This is going to be equal to 100 cosine of 30 divided by 170, and that's going to give us, mu of k is going to be equal to 100 cosine of 30 over 170, which is going to be equal to 0.509. I'm sorry, I'm having a very late night today, so you can already tell my vocabulary is dying. But the basis of this is that if we look back, we do have the answer choice of C, which is mu of k. Mu k is equal to 0.519. So that's nice. All right, our final simple dynamics problem. Yeah, this is basically only halfway through. How long has it been? 30 minutes? I hate everything. So let's work on this now. So we have our little, I can just draw it straight here. I'm assuming that you can pause. We have two masses, right? We have mass 1 and we have mass 2. We also have a frictional coefficient that is present on both both here and here, and it's the same on both surfaces, right? And so this is just asking for the acceleration of the lower block given a force and given all this, right? And so if we were to draw a free body diagram of all this, we can see that our M1 has its gravitational force of M1g and a normal force that's pointing up, right? And we also have our M2, which is going to be consisting of that original one, and it's also going to be consisting of M1g plus M2g, right? So we're also going to have a normal force that directly counteracts this, right? Let's say this is N2 and N1. So our total normal force that's going to be present is going to be M1g plus M1g plus M2g, right? Because it's going to be these two normal forces together that's going to be making up the normal force of this. And so our equation is going to be F equals ma again. So F net is going to be equal to our m, well, not our net force, our force, yeah, our F net is going to be equal to m2a2, right? So our net force is going to be the force that's currently pulling on it minus these normal forces, right? Which is going to be, well, not just these normal forces. Remember that our mu is going to be mu kn, right? And the reason why this works is because we have a frictional force here, and we also have a frictional force here. And both of these are going to be counteracting our force. So that's why our normal forces add together, if you were curious. So our total normal force is going to be our mu times g, which is present here, times 2m1 plus m2. And since we're trying to find our acceleration, it's going to be all divided by m2 as shown here. And so if we look back on our slideshow, that is going to be our answer choice A. So let's start moving on to our part 2, which is dimensional analysis, right? So here. So we're given a standard kilogram mass and a tuning fork that is calibrated in hertz. We're provided with a complete collection of laboratory equipment, but none of it is provided in SI. Which of the following could you measure in SI units? Acceleration due to gravity, speed of light in a vacuum, density of room temperature water, spring constant of a spring, and air pressure in the room. So let's look into this, right? So the big thing about this is that we need to remember about our dimensional analysis, right? So let's go to our scene and let's look over these, right? So we're given a kilogram mass, right? We're given a kilogram mass. Whoopsies. We're given a kilogram mass, and we're given a tuning fork, which is calculated in hertz. Hertz is 1 over seconds, right? It's also measured like that, which means that this is a measurement of time. So we're given these 2 dimensions, right? And we're told to try and find which ones work, right? So which ones do we have? We have acceleration due to gravity, right? First things first, which one is acceleration? Acceleration is going to be, our acceleration is going to be, can I find my mouse, please? Thank you. No, did not want that. Our acceleration is going to be here, and that is going to be LT, our length times time, divided by time squared, right? The next thing that we need to find, the next probable thing is going to be speed of light in a vacuum. Speed of light, that's going to be a velocity measurement. Oh, I don't know why it keeps on breaking. Next is going to be a velocity measurement, and that's going to be L divided by T, right? A length divided by time. Next, we're told to find the density of room temperature water, I believe. Density of room temperature water is going to be our mass divided by length cubed. Next, we're given spring constant, right? Spring constant, I'm going to switch to our scene. So our spring constant is going to be given as F. Oh no. This is a dilemma. Our spring constant is F equals negative kx, right? So our k is going to be equal to F over x, and we're just going to ignore this negative for now, right? So our force, if we look back on our chart, our force is going to be ml divided by t squared, right? So this is So this is ml over t squared divided by L, right? That means that we can cancel these 2 off. So our k is going to be equal to m over t squared, right? And finally, we're told, I think it's something about density, right? Our density is going to be measured as, our pressure. Our pressure is going to be measured as m divided by L times t squared, right? So let's look through all these options, right? Basically, we can already deduce we don't have a length measurement. We only have mass and time. So this, all of these 4 don't work. The only one that works is our spring constant, which uses only mass and time. So that's how we measure our spring constant, and that is our only available option if we look back on our thing. So it's going to be D. All right. Next problem. This is going to be a little bit more in-depth dimensional analysis, and this is probably not going to be encountered on the test, but it's just in case. So how does the speed of waves on a string depend on its mass, length, and tension force, right? So let's go back to our scene. So we know that we're told to find our speed, right? Our speed is going to be velocity. Oh no. Our velocity is going to be meters per second, which is going to be a length divided by time, right? Or you could say LT negative, right? Oh. We're given mass, length, and our tension force. It's not T, it's T here, but we would just say it's F, right? Haha. And so our F is going to be measured as, and if we look back on our chart, F is going to be measured as ml divided by t squared, right? So this is going to be this is going to be measured as ml divided by t squared, right? And so we have a t squared, we need a t. So what we do first is we know that we need to take the square root of our tension. And I'm just going to change this to tension for now. So we need to take the square root of our tension, right? That's going to give us the square root of ml times t, right? No. So square root of our tension, let's just say tension force, that's going to be square root of ml times 1 over t, right? So this would be like that right now. So what we can do is we can also multiply by L and divide by M, right? Inside our equation. So let's go back to this equation here. So we have our T. We have our L. We need to keep that L, right? So we have LT. We need to remove our M, so we divide by M. And so this is going, and we take the square root of this, right? So this is going to be equal to L times L, M times L over T squared times M, right? Square root. So we cross these out. This is going to be the square root of L squared over T squared, and this is going to be equal to L over T. Straight back here, straight back here, back to our velocity. And so that's how we determine it. So our final answer would be this, right? So it depends on it through the square root of L times T over N. Well, our T is our tension force, but you know, you get it. Ooh, whoopsies. All right. Sorry, I got jump spooked. All right, let's go back to our slideshow. Not our slideshow. Our other thing. Yes. Okay. So next one. How does the speed of waves in a fluid depend on its density rho and its bulk modulus b, which is measured in units of pressure, right? So let's first go back to our little helpful handy dandy dimensional analysis chart. So we need to write down our density and our pressure because those are what we need, right? So our pressure, our density is going to be measured through m divided by L cubed, right? And our pressure is going to be measured through m divided by L T squared, right? And our final, what we want to get to is, again, L over T. Whoopsies. I am not sharing the right screen. So if we go back here, these are the things that we need right now, right? And I know I'm slowing down. I'm getting tired. So let's first start, right? So we're probably going to need another square root here because our T squared is like that again. So first, we need to get L, so our final objective is going to be something like this, right? Where it's going to be L squared over T squared. Oh, isn't this handy dandy? If we just have our pressure divided by our rho, our density, that's going to be equal to L cubed, which is from here, times M. Well, okay, L cubed over M times M over LT squared. Isn't that convenient? We cross these out. This is now L squared. Cross these out. Now we're given L squared over T squared. If we just take the square root of all these, how convenient is that? Wow, we're given this. And this becomes this. And so, in the end, remember that this is B for bulk modulus. So, our final answer is going to look something like that. Right? And so that was a little bit more simpler, just because of how convenient that was. All right, let's move on. And so now we get to the error propagation problems, right? So our first problem. A student is measuring the surface area of a cylindrical wire. Radius is that. Our length of the wire is that. Okay, so precision can be measured in several ways. Which of the resulting uncertainties? How did they compare? So let's go back to this, right? So we have a wire that is measured with a ruler of 1 plus or minus 0.1 centimeters, right? So that's our uncertainty there, and then we also have another measurement, which is using a meter stick. We determined that the length of the wire is going to be 1 plus or minus 0.01 meters, right? Okay, so let's go from here. Our first option is to measure, to upgrade our ruler here to a caliper with an uncertainty of 0.01 centimeters, right? Our next option is to upgrade our meter stick to a tape measure with an uncertainty of only 0.001 meters, right? And that's coming from here. And third, we can repeat our measurement 10 times and average the result. So 10 times and average, right? So let's start. So our first option, it's going to make our uncertainty go in this direction, right? So we change it to this, right? And that's going to be, so since we're multiplying these two, our surface area is going to be directly proportional to our radius times our height. It's going to be directly proportional. It isn't exactly that, but it's here. So our first option is to, our uncertainty is going to turn into, remember our multiplication rules, we're going to have to go by the percentages, right? So what percent of uncertainty compared to that? So we can first do, so this is going to be 1% of this measurement, right? So we have 1% squared plus, again, this is going to be 1%, squared. And this is going to give us basically the square root of 2, which is around a 1.4% uncertainty, right? Next, we have option 2, right? And what this is going to do is we're going to have a 10% uncertainty here. 10% uncertainty squared plus a, what is this? So that's 0.001 divided by 1. That's going to give us a 0.1% uncertainty, right? 0.1% uncertainty. So that's going to give us so that's going to give us basically 0.1 squared plus 0.001 squared. And so that's going to give us a uncertainty of around 10%. And finally, we have 3, which is going to reduce our original uncertainty by a factor of 1 over n, right? And so 1 over the square root of n, right? So it's going to reduce it by a factor of 1 over the square root of n, which is going to be around 3 point, well, not that, square root of 10. It's going to give us 3 point, I'm pretty sure I'm doing this wrong. So let me just double check something. So that would be 0.1 squared plus 0.01 squared divided by square root of 10. Okay, so how this is going to work, sorry for the little delay. This is going to be our original uncertainty times, remember, 1 over square root of n, where n is the amount of attempts that we make, right? So 1 over n times the square root of, what is this, 10% squared plus 1% squared. So this is going to give us around 10% divided by the square root of 10, which is going to be equal to around 3.18%, right? Okay, so this is asking how they compare. We know that this is our highest and this is our lowest uncertainty, right? And so if we look at our answers, that is our answer. Answer D. All right, let's move on. So let me see if I can find my eraser and learn how to teach this class. Oh my god, it's already really late. Well, it's late for me. Probably not late for you. Alright, in an experiment to determine the speed of sound, a student took the measured the distance that a sound wave traveled to be 75 plus 2 centimeters, plus or minus 2 centimeters. Found the time that it took to be 2.15 plus or minus 0.1 milliseconds. Assume the uncertainties are Gaussian. The computed speed of sound should be recorded as one of these options, right? All right, let's go straight into it. So our equation is going to be v equals our distance over time, right? All right. So we have our distance, which is 75 plus or minus 2 centimeters. And I know I should probably do the significant figures. And we also have our time as 2.15 plus or minus 0.10 milliseconds, right? So remember that how fractional uncertainties work. So we're gonna have so basically how this is gonna work is we're gonna be measuring the percents, right? So let's start off with this. So let's take the square root of 2 over 75 squared plus 0.1 over 2.15 squared, right? And so if we take this into our calculator, we have 2 over 75 squared plus 0.1 over 2.15 squared. And that's going to give us around 5.4%. This is going to have an uncertainty of around 5.4%. If we were to plug that back into our equation, that is going to be, we know that it's going to be 75 over 2.1, well, no, it is not in fact that. It is going to be 75 divided by 0.0215. Nope, 0.215, sorry. It's going to be 75 over 0.215 because remember, this is milliseconds and this is centimeters. So we got to convert everything. So that means that meters per second, this would be basically 0.75 over 0.0215, right? 0.75 over 0.0215. Nope, one more zero, sorry. One more zero here. And now, if we just solve that, that is going to give us around 349. And we technically didn't even have to do this, since every single answer choice basically has the same number. We just need to find the uncertainty. So 349 times 5.4%, which is going to be times 0.054, is going to be equal to, so we have 349 times 0.054 is going to be equal to around 18.846, which is around 19. And if we look back on our slideshow or our questions, oh, that is the wrong one. Please don't look at that. That was very embarrassing because I did not have time to actually look through this, but we're going to get E, which is going to be 349 plus or minus 19 meters per second. So now we have our bonus problems. I'm sorry for showing that. I'm really tired. I don't know what I'm doing right now. Again, I really should not be qualified to teach, but I don't know what happened. So yeah, our final problem, this is one of the most heated debates to this day of an FMA problem, which is the helicopter problem from the 2014 F equals MA competition. So a helicopter is flying horizontally at constant speed. A perfectly flexible uniform cable is suspended beneath the helicopter. That sounds like a rhyme. Air friction on the cable is not negligible. So which of the following diagrams shows the shape of the cable? So let's think about this in parts. And there's even like a little clue here, which is to break down this problem. So we have a helicopter, we have a string hanging under it. So let's just take the very, very smallest, let's just say the very smallest component of the spring. Let's say it's like this, right? Let's just divide this into sections. Let's say that our string is composed of these little fragments that look like this, right? And we keep on going up all the way until we get to the top of the helicopter. So for this very bottom component, right, we're going to be having some force, some air friction here, and we're going to be having some force pointing down, right? Our gravitational force and our air friction force. So we can say FF, right? And so our final component is going to be in this direction. Our next component is going to consist of this component along with its own gravitational force and a frictional force of the same magnitude. So for these two components together, this is going to be having a, whoopsies. So if we were to look here, this is going to have a total component of one gravitational force and 2 of this friction force. So it's, again, still going to be the same direction. So all of these are going to continuously follow this rule until we have a rope that is pointing in this direction, right? For the entire rope, And since I'm currently, like, my hand is broken, this is the best I can do with the helicopter. Anyways, so that means our rope is going to be pointing in a straight line, which is going to give us the answer of B. So what if there was a hanging mast, which is the original intent of this problem? They just changed it. You can look into the lore on their website. Or somewhere else, I don't know. So what if there was a hanging mast? So let's take that little diagram. Let's say we have our little string. Let's take out the line tool. I'm too lazy to draw this properly. So let's say we have our string, right? We have our string, and we have our components, right? We have our components. They look like this, right? And we have a mast on the bottom. We have a mast. So let's look at this very bottom component, right? So we have this component here, and this is attached to a very big mass, or like a mass in general, right? We know that there's going to be a huge gravitational force here and a small frictional force here, right? Next component, this component on its own, it's going to have this small gravitational and a small frictional. And it's going to keep on doing that. So let's just add some arbitrary numbers in. Let's say that this force is going to be equal to, like, what, 10 units. This is going to be equal to 1 unit, and these are all going to constitute to 1 unit, right? This is definitely not accurate, but it's what I'm going to be going for, right? So let's just analyze the slope of every single component, right? So on the first one, we have 10 over 1, right? Next, we have 11 over 2, 12 over 3, 13 over 4, and you're going to be realizing that this slope is basically like starting to flatten out almost, right? Where if you look at the slope, it's going to be first like that, then like that, then like that, until it reaches the top, right? So if we were to draw out a diagram of what every component would look like, as we go up, it would start curving until it reached something like this, right? And if we look back on our questions, we see that that would be our answer choice D. And so that's basically it. I did not expect for this to go for so long. This has almost been an hour, but here's all the solutions. Thank you so much for watching. Please do not shame me for actually looking up the answer, because I have not done this beforehand. But yeah, thank you so much for coming. Please enjoy, and I guess I'll see you next time. Thank you so much. Have a great day.